Okay, here's a wild thought for you. What if the way our brains learn isn't just about psychology, but about physics? Today, we're going to explore this really mind-bending idea that learning follows the same basic rules of efficiency that guide, well, everything from a thrown ball to a beam of light. So let's dive right in. All right, so let's kick things off with a bit of a puzzle here. What could a thrown ball and a learning brain possibly have in common? I mean, on one hand, you've got something that follows a pretty simple, predictable path. On the other, you've got maybe the most complex object in the known universe. But what if, and this is the key, what if they're both playing by the same deep, hidden rule? And here's the answer. It turns out they both follow a path of least action. Now, what does that mean? It means both the ball and the brain are, in their own unique ways, basically taking the path of least resistance. They're trying to minimize this thing, this physical quantity called action. And, this one idea, it might just completely change how we think about learning itself. Okay, so to really wrap our heads around how our brain finds the path of least cognitive effort, we've got to back up for a second. We first need to understand how nature itself, just the universe, finds the path of least action. And for that, we're going to take a quick detour into the world of physics. So in physics, this thing called the principle of least action, it's a huge deal. It basically says that nature is, well, kind of lazy, but in a really smart way. It's always looking for the most efficient route. A perfect example is light going from air into water. You know how it bends? Well, it does that because that bent path is actually the fastest way for it to get where it's going. It's quicker than a straight line would be. Nature is just constantly optimizing, always finding the path that costs the least amount of this action. Right, so how in the world do we connect light rays and baseballs to the incredibly messy, complex business of learning? This is where we make the big leap. What if our brains, in the very act of learning, are also following this universal law of efficiency? So this is the central idea right here. Just like physics has its principle of least action for physical objects, this theory proposes a principle of least cognitive action for learning. The implication is huge. It suggests that learning isn't just some abstract process happening in our heads. No, it's a physical process, governed by the exact same drive for efficiency we see all over the rest of the natural world. I mean, this really reframes the whole concept of learning. The researchers put it this way, quote, "The emergence of learning is viewed as the outcome of natural laws that govern the interactions between intelligent agents and their environment." So we should stop thinking about learning as just some clever trick our brains figured out. Instead, we should see it as a fundamental law of nature, something that just happens when an intelligent thing interacts with the world around it. Okay, but for this whole analogy to actually work, we've got to figure out what energy and action even mean when we're talking about a brain, right? If a mind is minimizing something, what is that something? Well, the theory breaks it all down into two competing cognitive forces. So, first up, we've got something called cognitive kinetic energy. The easiest way to think about this is it's the cost of changing your mind. It's that mental friction, that effort you feel when you have to update a belief you've held for a long time or learn a totally new skill. Every single time your brain has to rewire its connections, it's spending this cognitive kinetic energy. And then on the other side of the coin, you have cognitive potential energy. This is basically the penalty for being wrong. So let's say your internal model of the world says it's sunny outside, but then you step out the door and get totally soaked by rain. Oof, that's a high potential energy moment. Your beliefs don't match up with reality, and the environment is basically pushing back, telling you, nope, you're wrong. And this is the crucial part. Learning is just a constant balancing act between these two energies. Think about it. It's hard to change your mind. That costs kinetic energy. But it's also really costly to be wrong. That's high potential energy. So the brain is always trying to find that sweet spot, that perfect equilibrium that minimizes the total cognitive action. It becomes this beautiful, self-correcting process, always settling toward a state that's more stable and more accurate. All right, so when you take this really elegant idea and you try to translate it into math, things get, let's just say they get a little complicated. But don't worry, we're not going to be solving any differential equations today. Instead, we're going to use a simple metaphor to understand the really cool insight here. So the math behind all this leads to something called fourth-order differential equations. And yeah, I know, that sounds incredibly intense. But all fourth order really means is that it's tracking 4 different levels of change all at the same time. Let me show you what I mean with a simple analogy. Okay, let's imagine a learning vessel, like a ship, that's trying to navigate a constantly changing sea. Step 1, the most basic level, is just tracking its position. Where is the ship right now? Step 2, we can add velocity. How fast is it going and in what direction? Getting better. Step 3, we can track its acceleration. Is it speeding up, slowing down, turning? This is what a lot of physics deals with. But this is where it gets interesting. The fourth step, the fourth order part, is about tracking how the ship adapts its entire strategy. It's not just changing its acceleration. It's changing how it decides to accelerate based on new data. It's not just steering, you see. It's learning how to become a better steerer over time. So, okay, this is a really beautiful theory. It's elegant, but is it actually useful? What's the real-world payoff here? Why should we care about framing learning in the language of physics, especially when we're talking about something practical, like AI? And this is where it all connects back to the real world. This grand, complex theory isn't just some abstract idea for a paper. It turns out, when you take these complicated equations and apply them to a simpler, more standard supervised learning problem, they actually simplify down to the classic algorithms we already use, like gradient descent. And that is a huge deal. It shows that this framework is robust. It doesn't just describe some new thing, it actually contains our existing tools, and it gives us a deeper physical reason for why they work so well. So, what are the big takeaways from all this? First, that learning might not just be a biological thing, but a fundamental law of nature. Second, it's this dissipative, self-correcting process, a constant balancing act between the internal cost of changing your mind and the external penalty for being wrong. And what's really powerful is that this framework assures us that a minimum and optimal learning path always exists. This makes learning a well-posed problem. And finally, it provides this incredible, deeper framework that can actually encompass the classic AI algorithms we use every day. And all of this leaves us with one last, pretty profound question to think about. If learning truly is a universal law of nature, if it's a drive toward efficiency that's baked right into the fabric of reality, where else are we seeing it? I mean, could it be in the way an ecosystem adapts? Or in the way an economy fluctuates? Maybe even in the evolution of entire galaxies? What else in this massive universe is learning right alongside us? Thanks so much for joining me for this one.